Right. Thank you for having me. I'm glad to share some of the things. When I started um, about 8 years ago, when I finished my undergrad, my first project was actually in timber, which is the sauna, one of the projects that I'm going to be talking about. So I was right at the spot you guys are right now, where I was trying to figure out how to make this. So I think I would be glad to share some of my experiences, and hopefully you guys learn from it and can do better, because obviously we always want to be pushing and always want to be doing better. A little bit about our firm, just to give you guys a little bit of background. I'm a designer in a firm called PARTISANS. We're an architecture firm in Toronto, Canada. And we sort of specialize, we don't really specialize in any kind of projects, but we do really ambitious projects that focus on, a lot of it focuses on fabrication, working with fabricators to really achieve some spectacular ambitions for the client. And so there isn't like a specific typology that we do. We've done everything from saunas to bars to product design to residential to master plans. But really what I want to focus on today is the two timber projects that we did and sort of walk you through the process, design process, how we approached it, and talk about some of the challenges that we had and how both of them came together. So I know that this is not like the typical timber projects that you see today on a mass scale. These are more on a smaller scale and focus more on custom fabrication. But I think a lot of the principles, they do scale. And a lot of the larger projects will apply some of the same sort of thinking and some of the same processes that we did here. So I think there's, even though it doesn't necessarily represent like a large-scale project, I think some of the thinking is directly translatable. So really the basic process, the way you approach like a timber process, timber building is, I mean, in general, it's fairly simple. Really, timber in specific, when you're doing a project that's material specific, really what you need to do is understand the material first. So timber is unique in its characteristics and it's different. It behaves differently from, let's say, concrete or steel. So really understanding what those limitations are, not only with the material, but with the fabrication capacity, can guide your digital models and your designs. You can create sort of like design parameters around those restrictions that will feed into fabrication and sort of and delivery and install. So altogether, what you see a lot today is that companies, design companies and fabricators and engineers, they always started to do these kit of parts. So everybody has their own kit of parts, and they develop connections, they develop processes of how to manufacture it. And really it's based on these 4 categories. There's no one correct way to do it. There's multiple ways, but I'll walk you through some of the strategies that we did. So focusing first on the grotto sauna. This is a small project we did about 5 years ago. We had a client with a property in sort of just a few hours away from Toronto in the north along the Canadian Shield. And this is sort of a part of Canada where it's a large sort of bedrock plateau that after the Ice Age sort of gets stripped of its soil. So what you see on the land is just like rock, and wood, typically cedar. And so this project became about how do you not disturb the sort of the serenity of the space, but at the same time respect the materials and also create a sort of this wonderful sanctuary in the middle of the space. And so we proposed this design to the client, and he loved it, and we were going to go ahead with it. But the challenge is that how do you get there for something like this? So with timber, timber is a unique material and has its unique properties. So one of the things that it's limited is in shape and size. So it comes from trees, and typically nowadays you actually cut it down from smaller and smaller trees because you can't really wait too too long for larger pieces. So what you're dealing with at the onset is limitations in size. So that's one part of working with timber. The second part is that the material is a live material. So it's a fibrous material. It's made out of thin strands that grow up and down the tree. And what that means is that the material behaves differently, let's say in the lengthwise direction than it does crosswise direction, right? So what happens is that it can deform. Not only performance-wise, not only is it different in compression and tension, but it will also distort differently depending on how you cut it and how you piece it together. And the third quality of timber is that it's hydroscopic. So it means it behaves differently with the amount of moisture and heat that it has. So it's a live material, so it moves around. When there's more humidity, when there's more heat, it expands. When there's less so, it contracts. So you're always dealing with these parameters and trying to figure out how to give it enough tolerance and how to piece it and orient it together in a specific way to create the desired effect. So in terms of dimensional sort of restrictions, typically the way the process works is that you take a bunch of the pieces, you fasten them together in some way or laminate them together in some way, and then you mill it to the shape you want, then you kind of put it together. That's the basic strategy. And there's a lot of different ways that come out of ways of laminating things together. Like if you laminate something with glue, you create glue lam. So you use like an epoxy or some kind of adhesive to keep them together. It behaves differently than if you fasten them with like a dowel, where it's more of a mechanical joint rather than like a adhesive joint. And so what you see now is a lot of these denominations of timber structures. You have like CLTs for cross-laminated timber, you have DLTs for dowel-laminated timber, glue lam, and so on. And really the difference is in performance and differences in process, right? So depending on the limitations and depending on the context that you have, one approach might be more suitable than the other. And I'll describe to you some of the challenges we had with our project as well. The other issue that you have, and this returns to the fact that it's a very directional material, is that really when you put them into blocks, you have a choice. Like you can either cross-laminate the joints as what you see on the left, or you can laminate them in the same direction, like what you would see in glue lam. And performance-wise, they behave differently, but also aesthetically, they behave differently. So in typical glue lam buildings, when you see big slabs that are rectangular, you don't really notice any of the interiors of like the lamination, any of the interior layers. But in a project like this, when in the sauna, you do notice, because you're carving away, you do notice every single piece, especially for the thicker pieces. So the trick becomes also in the way you laminate them and the way you coordinate the lamination process. So for the sauna, for example, because we wanted to manage some of the deflection, and also the aesthetics, we wanted to orient all of the boards and all of the sort of individual timber pieces in a specific direction. So if you look at the image on the right, once all the pieces milled and milled in a specific orientation and position, the lamination seams align. So it creates an aesthetic effect, that's one, but it also, what it means is that the seams that we're creating in between the panels deflect uniformly, right? So because they're aligned in the same direction, that seam you wouldn't really have like a thicker seam at the top and thinner seam at the bottom. When the wood expands and contracts, you would have a uniform width. So that's one thing to consider, because it's something that you set up in the beginning that has a dramatic effect on the final aesthetic of the project. And so this is an example of something we tried in terms of lamination. So on the left, you see the piece laminated with an epoxy. So this is what you would have typically in like a glue lam structure. And then on the right, we tried something more akin to a dowel structure. It's a little bit different. It actually uses a dovetail, a dowel, to laminate them or fasten them in the same direction as the unit. But really, the reason we investigated these two is because a sauna is a unique sort of environment where the heat goes up significantly and goes down significantly really quickly. And what that does to the material is it makes the material expand and contract really quickly with all the moisture. And that actually creates significant issues for the panels. So one thing we discovered is that when you, the material will always move, and you can't really neglect that point. You actually have to play into it. So when you use a really hard epoxy, when we're trying to really keep the rigidity of the piece together, like what you have on the left with a glue lam structure, it does not allow enough flex for the natural expansion and contraction of material. So what happens is that the wood breaks, right? So the seams stay together because the glue is stronger than the wood, but then the wood ends up cracking. So we thought, well, and then in addition to that, the other issue is that a lot of these epoxies are not meant to behave at high temperatures. So what you have is that I believe it in some cases like 80 degrees or 60 degrees Celsius, these materials break down and emit VOCs, which is not great for a sauna as well. You want to keep it natural and safe. So we also tried the Dowel approach, closer to what you see on the right, where we thought, well, you're not emitting any volatile compounds by heating the material because it's all wood. But the issue with this is that the there's no stability between the joints at the top. So what happens is that even though it doesn't crack in the middle, the individual lamination seams spread apart and chip away and things like that, which typically would not be an issue if you have a beam, let's say 6 meters up in the air. But when you're sitting against it and you're in constant contact, this becomes a hazard for use. So what we ended up finding is a marine type of epoxy that actually provided enough flexibility that you can mill through it, and it allowed for the expansion of the joints, but also kept it glued together, like closer to what you see on the left, sorry. And so all of these investigations, I've covered just a few, but there's quite a bit in the process. You use those to create your design parameters, right? So like, for example, the dimension of the wood that we were able to get was very specific because of the local supply that we had. And that determined our panel sizes. So because we used nominal dimensions, we used dimension lumber, our panels were usually determined whether they were like single ply, a single thickness of the material, 2 thicknesses of the material, 3 thicknesses of the material. And then, so when we developed the shape, for example, they would be done to these restrictions. The other issue that you would have when you're starting to put all of these design parameters together is the challenge of installation. So at this stage, you're sort of combining 2 things. You're combining the material studies you did in the past and trying to make the shape conform with the fabrication limitations. But at the same time, you got to think about how all of this comes together. Because in some applications, when let's say it's a 1 surface or 2 surfaces, it's not too difficult. But when you're trying to wrap it around an entire sort of interior of a space, sequencing becomes quite a bit of an issue, right? Because at some point, it's like a 3D jigsaw puzzle where sometimes you won't be able to fit a piece in if you don't put it in the correct order. So personally, I find some of the more interesting parts about these projects, about the sauna, is actually the back. A lot of these panels are actually chamfered in certain ways that they can slide in at a certain sequence. So in the front, you create an illusion of this continuous space, but at the back, there's a lot of sculpting that happens in order to make it happen. And the other thing to point out is that at this point, the project begins to become fully digitized. So while we're doing the studies and trying to find the limitations of materials, all of our models are being produced digitally. The other element of this is to the digital process is how we communicate with the fabricator. So we work closely with a local fabricator on both of those projects. And one of the things we found was that typically the way we would do things is we would give them the geometry. So let's say a panel, and they would run it through their CAM software, which would create toolpaths. So these are sort of like the back and forward paths that the CNC mill would take in order to route out the material. And this worked fine for most of the panels. That's how we did them. But for these more complex panels where we needed vents in the seating, feeding them the geometry, so the actual modeled geometry of the vents, actually proved quite problematic because the software was not trained to do it very efficiently. So what could have been done in a simple dip sort of movement of the router, it was trying to do in about 100 or 200 individual sort of back and forward movements, which added about 4 to 10 times the amount of time needed to mill a panel in some cases, which was not realistic for our time schedule or cost schedule. So we thought, you know, a better way to do this was to be sort of like short circuit the process and just do those paths ourselves. So we developed a simple script, essentially the dips for the vents, and we fed them in conjunction with the actual panel. So these are the two sort of raw inputs that went into the CAM software. One was the geometry, the reference geometry, and the other one was the sort of the tool paths, and that sped up the process dramatically. So that was sort of our first sort of try at hacking the process and sort of getting more involved with the process. But the more we did it, the more we found that, you know, if you want to be effective in this sort of manufacturing technique, you really have to be involved and you have to write your own paths. You have to write your own control code. And so that's what you see on the left there, where the router is sort of taking up the bit. One of the other things to consider is the availability of machinery. So locally, we have a very healthy millwork community in Toronto. A lot of these machines are used to produce millwork or cabinetry. And so there's a lot of three-axis CNC machines. At the time we started this, the only 5-axis machine that was in Toronto was with this one fabricator. So in order to speed up the process, one of the design criteria is that we had to separate about 70% of the panels to be able to be cut on a 3-axis machine, and then the remainder on a 5-axis machine. And what that allowed us to do is really to distribute a lot of the work so that we can do it faster. So, and these really would, that's one thing to consider that's really sort of unique to every, I guess, manufacturing ecology. For every country and every region will have their own sort of capacities. And I think it's important to really understand them in order to be able to do this effectively. And so the last remaining portion is, how do you piece all of this together? I mean, this is probably one of the more complex ways to apply timber, but I think it reveals some of the sort of gaps in the processes that we see now that I think can be handled with automation and digital practices. So Like I mentioned before, these were really 3D jigsaw puzzles, and sequencing became an issue. We did a similar project in Poland, and one of the issues was communication. How do you communicate the sequencing, and how do you communicate the fabrication specifics to somebody abroad and through sort of universal means? So what we did was we actually created fabrication sort of guidebook where the specifications for every piece, everything from what the piece looks like to how you block it out and how you laminate the base piece, and then the origin and sort of how the pieces come together, all the sequencing. We created a sort of a booklet to communicate all of that. And that's how these projects came together. Really, as you can see here, these projects aren't put together by robots yet. There's a mallet there, and that's because these were done by craftsmen. But increasingly, you notice, and we have this problem in Toronto, where the outlook for the next 30 years is that we're going to have an issue supplying labor, specialized labor. And so I think some of these digital means of facilitating installation are going to become much more important, because you're not only going to have less labor, but you're going to have less skilled labor. And so you're going to have to communicate how to build some of these things in a much simpler and coherent way. And so when you do all of that and you apply all those strategies, you can get in effect something like this, right? Where everything is sort of thought through and it comes together in a fairly quick way. Our is a little bit different. So I'm not going to repeat some of the things that are already described in the sauna. We applied some of the same sort of lamination and fabrication technique, but what was unique about this project is that we had to work with a material that was much harder. So the client, when the client came to us, he wanted a bar that was not only world-class, but also lasted for 50 years. And this is also, it's very different mentality than what you typically have in Toronto, where the turnover for a restaurant is typically a couple of years, usually like a lease length, so like 3 to 5 years, and then you change the interior. Well, the client wanted something that lasted longer. So we chose a harder material, mahogany, to make all of these panels which would last longer. The issue is that applying the same methodologies doesn't really work. Carving a soft material versus a hard material is very different. And so this project actually involved quite a bit of research and development in order to get the process tuned in order to do some of this work, and also on budget and in a timely manner. So again, the question became, how do you do all of that with this? And so the clients were very interested in these textured surfaces. They were all tattooed, and this was the first Spanish tapas bar in Toronto at the time. And so they wanted to draw an inspiration with Gaudi and sort of these flowed surfaces. And these were some of their preliminary sketches with that sort of inspired some of the geometry. But eventually the geometry evolved into these shapes of like tendons and muscular twisted geometries. And all of this was a continuous T-spline. We did it in Rhino and T-splines in the time before it was bought by Autodesk. And so it was modeled as a continuous surface. And then the question becomes, how do you take this pristine digital surface and then you actually fabricate it out of these discrete lumber components, right? And then we have the same issues with the material that I've described before, except now it again wraps the surface three-dimensionally, so it has to join in all sorts of directions. And we're dealing with a harder material to CNC, a more costly material because it's a harder material. And so how do you do this not only how do you do this, but how do you do this efficiently? And so we're looking back at some of the sauna work. This was a year after we did the sauna. And we thought, well, can you do the entire project out of toolpaths? We found the process to be very efficient. So instead of texturing and modeling the geometry into the surface, can you produce the texture using toolpaths? So can you circumvent the entire production process that typically happens and sort of feed the machine directly the sort of the final geometry that we want. And so we took that and we applied it to a surface. So what you see here is, I believe, about 10 kilometers worth of toolpaths that wrap all around here. And so each one of these was, you can imagine that the surface was, first of all, sort of broken up typologically. So it wasn't a continuous surface in a way. Like a surface has a Y, sort of a UV component to it. So all of these surfaces were actually broken into these continuous bands. And we were able to map the toolpaths along these bands. So that's really the basic logic for it. Except the bands didn't really happen, they were not panelized, they were continuous bands. So you can see here on the right, one of the bands spanned across the entire space. So there wasn't any logical way to break them up, but the good thing about this is that we were able to really control how much detail each piece got and each section got, but also how fast each piece got milled. So in the diagram above, you see sort of two different densities and then sort of a transition between the toolpaths. So when you space the toolpaths apart further, it mills the material quicker. So the panel mills quicker because there's less paths, whereas, and it creates like deeper scallops. When you put them closer together, you get a smoother finish, but it takes much longer. So we had a limited production schedule, and we tuned these toolpaths in a way that allowed us to speed up certain areas that, let's say, it didn't need too much resolution and use less toolpaths. The issue was that the machine that was in Toronto at the time, it was a 5-axis machine, but it was not built to handle some of these complexities. So we mapped all of these toolpaths against the normal of the materials, which allowed us to really control the scallops and also control the speed of the process. But the issue behind that is that what we found is that these machines, even if there's like a slight discrepancy in the surface and the line, I think we were working at a tolerance of something like 0.000 millimeters. But even that small discrepancy, if the curve was above the reference surface, the mill head would flip 180 and try to cut the material from the inside of the surface. And so what we originally had is these big panels that were cut, and then at a random point in the code, the mill would flip and cut the material from the inside, cutting the panel in half, virtually ruining the panel. So we had this quite a few times. A couple of times the machine cut through itself. It tore up the suction cups. So there's quite a bit of issue trying to make this work. But we were working with the fabricator and the manufacturer of the machine. We were able to patch those differences with a few updates. But at the time, to get this to work was quite of a struggle. And I think once you don't realize how much work actually goes into this until you actually try it. And so when you try to create your own control code, you notice that a lot of times it's not the bottleneck of creating it. It's actually the bottleneck of interfacing with a lot of these machines, because each one reads the code a little bit differently. There's no standardized version. So brings back to the point that I was mentioning earlier, really important to understand not only the material, but sort of local capacities that you're dealing with, and really understanding their machines and what you can do with them. So after we got the general, let's say, proof of concept done on how we're going to fabricate this thing, the next issue was, how do you break that surface up? And how do you maintain continuity, but also fabricate this in an efficient way? What we found out with the sauna, typically the way things happen when you give it to a fabricator, so they take each panel and they create sort of like a bounding box, right? So if you have a square panel, not an issue, because that becomes the bounding box and it is pretty efficient. But when you have a sort of, let's say, a custom or more irregular shape, the bounding box is a very inefficient way of laying out the materials. Typically, the way the sauna panels were done, there was a bounding box, and then the material was milled in profile, so in plan, but then the material was also milled out in 3D. And so what ends up happening is, when you do it this way, there's a huge loss in material. So there's in a typical sauna panel, there was about a 60 to 70% loss of material, because you're carving it away in both directions. So we thought, for this, because we're dealing with mahogany and it's a much more expensive and tougher material to mill, we wanted to minimize the amount of milling that happened and the amount of waste that happened. So we devised a strategy of breaking up these panels, and in a way where, not only are they stacked in different depths, so like in yellow here, you would see that those are single ply pieces, blue are two ply pieces, and sort of the big transition pieces are 3-ply. But we also created a little script that controlled the actual blocking. So we created an instruction of how do you block each panel using standard, let's say, size modules in a way that's more efficient, right? So when you're lining it with the machine and you're cutting it, you're not wasting as much materials. So there's two benefits of that. One is that you can do it faster because there's less milling. Two is that you're using less material. And three, you're able to do quantity takeoffs early on. By running the script through all the panels, we're able to know exactly how much wood we needed. So that was our way of dealing with the situation, which was a little bit better. I think this way, doing it this way, we reduced the amount of lost material to something like 40 to 50%, which is not perfect, but I think you're always going to have this issue when you're dealing with irregular shapes. So I think that was an interesting approach. The other challenge that we had is, how do you seam these panels? What we learned in the sauna is that the way you actually seam these changes the way that they deform. So this is a hydroscopic material again, and so with different humidities and different temperatures, they deform. And so what we found out that the angle at which the seams intersect makes a big difference. So when you have, let's say you imagine an oblique connection where one angle is obtuse and one angle is acute. Because the obtuse sort of corner has a lot more mass, and intersected these seams at a particular angle. When these, sorry?
Could you please repeat the last part? Because I think the connection just went out. Or...
Yes, sure, no problem. So what we found out is that when we, a simple linear connection, like if you divide the seam in a very kind of straight way, you create obtuse and acute connections. And what happens is that because they have different mass or different volumes, they deflect different ways. And so if we had acute and obtuse connections at every seam, what you would have is that over time, as there's more or less humidity, these panels would contort in a way that it would misalign very drastically, actually. And so we created these connections, like these C and S connections at all the panels, which were really what they created is a perpendicular to connection at every edge. So every edge had a perpendicular connection, and by default, every edge had the same amount of mass. So when these panels did deform with changes in temperature and humidity, what happened is that they deformed uniformly, right? So they deformed together. And so even though they might have moved a little bit in, out, up, or down, they moved together, so you still maintain continuity. So really that was the trick with this seaming. Again, you will typically not see these issues in let's say like a typical timber structure, because a lot of the members are rectangular. But once you start to move into custom elements, some of these issues become more apparent. So I think it's something to keep in mind. And again, these were milled sort of in a similar fashion, where they were just done on a CNC mill. But the last consideration that I would sort of remind you guys of is to consider the weight and how these will be fastened. So we were working with a denser material, a harder material, which means that the weight was also heavier, because the density was heavier. And so it's easy to, let's say, break up these panels in 3D. And there's like logical stops where you want to do them because of all these factors that we just discussed. But the last factor to consider is the amount of weight. So there are panels that we couldn't really break up any further because of the way they transitioned and then deflections. So some of these panels ended up being about 200 pounds. It's quite substantial. So something that, let's say, 2 or 3 people would have to lift into place. Right? So these are small projects. You didn't have robots, you didn't have cranes that lifted them into place. It's still a human element. And so at some point we had to go back to our design process. That's why we showed that as a circular sort of thing, is that at some points we calculated the panels were too heavy, and then we had to go back and figure out a different way to seam them. Even though all the factors work perfectly, the weight component just added too much complexity into the installation process. So you're always having to do these circular motions. Again, we learned from this the hard way. Hopefully you guys don't have to do this, but just keep it in mind, really understand the properties of the material, because it does, and think about sort of the end component and how they're delivered, as well as understanding it from the small scale of how the material behaves. And so when you do this, hopefully you end up with something like that. I think if you look at the picture, both of the pictures, really the trick here that we're able to achieve is that even though there are these highly textured panels, the textures align perfectly between the two panels, and they sort of behave in unison and things like that. So your wood, we find, is quite an amazing product, and it's quite a flexible product. You can do quite a bit with it if you really pay attention to the way it behaves. But I think, it has its own limitations, and you have to work through them. So I think really understanding the materials and creating systems where panels come together and work together, I think is going to be the next interesting part. I think really focusing on, I don't think there's another way of doing this than a purely digital process, because there's no, because of the economies now and because of the complexities, that seems to be the only way you can actually move forward. So I think I would, if I was you, if I was 5 years ago, I think I would definitely invest in some of these sort of digital workflows and really think more about how you integrate with the manufacturing aspect of it if you're interested in a material. I think it's going to become critical not only for fabrication, but also for controlling the installation process. And all of that will affect cost and your ability to actually realize some of these projects. So I hope that was useful. I know there's going to be a questions period at some point. I'll be happy to answer. I mentioned this to Lance, that we also have a mill worker that worked on this that's willing to answer questions as well. So if anybody has any technical questions and specific things, I know I sort of glossed over a lot of the technical aspects of it and in the interest of time, but if anybody has any technical questions, we'll be happy to answer it. And yeah, hopefully you guys pursue this and go further than we did. So, thank you.
Well, thank you very much for your presentation. I think we can all agree on that was very useful to our students. I think that you gave very helpful tips, which will bring our students further. Yeah, so if, like Ivan said, if you have any questions, please leave comments or yeah, leave questions in the comment section. Yeah, and I would like to thank you again for meeting with us and sharing your knowledge. And yeah, and I will hereby end this presentation then.
Well, thank you all, and good luck. I'll be happy to see and to keep track of what you guys are up to. I mentioned to Lance that really interested in the course and seeing sort of like keeping tabs on it and hovering over it. If there's any other presentations, I would love to sort of even sit in and listen in. We're very interested in the subject, and I think even being passively aware of what's going on is very helpful. So just let's keep in contact and let's keep pushing.
Please, really, this was so inspirational. Wow, thank you so much.
Yeah.
It really was.
Thanks very much.
Wow, I'm really blown away. I really am blown away.
Yeah, it really shows how big the challenge is to design with timber. It's not easy, right? Yeah.
Yeah, it's not easy, but the result is so beautiful. It's really, and also I was, because you were talking about that it is mostly handmade, all big panels, right? Yeah. Okay. I can hear myself again.
Yeah.
I can.
It's Lance mic again.
Yeah, it's Lance mic again. But that all those panels are made by hand and then put together. Oh my God! It's so. This is really something I think that a lot of people are not aware of. That this
I actually
exists.
have another question. Like when we were constructing this bar and you were talking about the weight of the different what's called
Panels.
Yeah. Did you actually calculate that beforehand, or was it sort of trial and error of like, yeah, this panel is actually way too heavy to handle in this space with just 3 or 4 people?
We did calculate it beforehand, and we knew they were going to be heavy. I mean, there's easy process that you can do. We had the material in hand, so we could weigh it and estimate general density. And using density, you can apply that into a script that translates volume and density into weight. It's pretty rudimentary, but we had this. You sort of imagine that there's not one correct way to do it. So at some points we had to go with heavier panels in order to hit some of the other checkboxes, in order to make it work and aesthetically, in order to make functionally and performatively So it's a trade-off, right? But
you have to balance it all the time. Yeah.
Right. And then I think building yourself tools. So we use a lot of Grasshopper because it just worked really well with Rhino, but building yourself these little tools that keep track of a lot of this and just being aware of it, I think is half the work, right? A lot of times the worst thing that can happen is you're not aware of a particular challenge, and then you have to scramble in order to figure it out later when the panels arrive on site. So I think being cognizant of all the little elements, and you won't, get them all in one first project, but I think, building up the repertoire, learning from other people, I think you can start to capture a lot of these little elements.
I have a question as well, because when you get to use the wood in, because of course in an interior you're gonna either like spill something over it. Is there a special finish, or how do you make sure that it remains durable and stays looking nice as well? Yes.
So in the case of the sauna, you can't really put anything on because it won't really last anyways. You don't want any kind of finish because you don't need any kind of finish. Really, the only contact that you have is like sweat and water, and so, which is typical in a sauna. For the bar, it's actually a good point because you do have drink spillage, you do have water spillage, and as you see in the last image, people love to touch it, and so you have a lot of hand oils. And actually, one of the original samples that we had got touched so heavily that it actually stained it. So I think for this one, because it had to be food safe. There's a lot of products where you can seal wood. The issue becomes when you're in a restaurant setting, it has to be food safe. Because people will always have their hands on it. You'll have things like napkins that might be on it, like fruit, as you see here. So we used a natural oil-based, it's not a lacquer, it's kind of like an oil finish, which actually part of the reason why these panels look so rich. This isn't Photoshop, the saturation isn't up. It's actually the oil finish that really brings out the vibrancy in it. But they have to be reapplied every year, right? So I think some of the more stronger ones, let's say, they're not food safe, right? And you can reapply them every couple of years, every 5 years, but they're not food safe. So something like a commercial setting or like a beam or a ceiling, you might be able to do this or not finish them at all. But if it's in constant contact, it is a porous material, so it'll take in hand oils, it'll take in water, and so on. So protecting it becomes an ongoing process.
I see, yeah. Good to know. You really have to
I
take
have a question as well. What you are doing is almost a digital craftsmanship. It's kind of redefining the role as an architect. So are you also working more on specializing in these digital techniques and maybe also producing these blocks yourself? So are you investing in a CNC machine, for example, or something like that? So more doing these design and build projects.
We focus more about building collaborative networks. We know that we won't be able to do it all ourselves. We're not only interested in wood. We do a lot of different projects. Recently, we did a project, I think it was published recently, called Gusto 501. It's out of terracotta block. So we're more interested in the manufacturing process and design processes than we are in a specific material. So for that reason, we prefer to work and create close networks with fabricators. So we don't need to buy our own machine. If we need to test something, we work with our fabricators and engineers and do it that way. So I don't think that's the only, there's no one solution, and it also depends on your network. If you don't have anything locally, I imagine it would be very difficult to collaborate with a fabricator. So you would probably need an in-house piece of machinery to actually develop something. But because we have the relationship, it's not needed. A lot of, there's a big issue with capital costs, especially getting some of these machines, because it's not only the cost of the machines, but it's also the cost of facilities to house them, the cost of maintaining them, the cost of training, and the cost of filtration systems and things like that. It quickly is very unobtainable for a small firm or a medium-sized firm, and you would need like a steady flow of projects in order to make sense of it. So something like in an institutional or a university setting, it might make sense because you're always learning and researching. And something like if you're a fabricator, it makes sense. It's more difficult to justify in an architectural setting, we found. I think some governments make it easier with more research funding. Some governments make it more difficult. Canada, I would say, is in between. I think we work closely on several projects and we're able to achieve some interesting things with it, but it always really depends on the circumstance. I think architecture is a little bit, I would say, inward looking. Like architects are always thinking about architecture, but when you start looking at these systems, it's more than that, right? It's more about fabric. It's fulfilling the entire thing. It's fulfilling shipping and handling. It's fulfilling maintenance. It's fulfilling economies of scale and economics and governments. You know, so I think there's no one perfect solution. I know I went on a bit of a tangent, but I think really the next role, in order to bring these things to the next level, I think we have to look holistically and beyond the architecture industry, and really look at how things connect on a larger scale.